Welcome back to our ongoing series on trigonometric identities and equations. In the last couple of videos we've been looking at identities. Actually, for the last several videos that's what we've been doing. And identities are, of course, are equations that are always true, but that's not usually the case, right? A lot of equations are not always true. And so in these next couple of videos we will be looking at what to do in those instances. So first off, we'll look at kind of equipping ourselves with how to find general solutions to equations, and then in the next we will have kind of a sample plate of various types of equations that we can use various techniques to find the general solutions to. So let's go ahead and get started. Right, so far in this chapter, actually so far for a very long time now, we've been concerned with identities. Every time we saw an equation for a while now, we've tried to tell ourselves, okay, I'm looking at an identity. What do I have to do to make it be an identity? How do I turn sine squared plus cosine squared equal to 1 in this case, right? What do I have to do here? Of course, not much, right? This is just true, right? This is just a Pythagorean identity, but that's kind of symptomatic of what we have been doing. That's been our big concern. How do I go from the left-hand side to the right-hand side to get always true? But not every equation is always true. In fact, most aren't, right? Suppose I had cut out this cosine squared term and gone down to just the equation sine squared equal to 1. Well, that's not an identity, right? I can think of countless values of x that I can put in there to not have this be true, right? For instance, x equals 0 would knock that out. But I can still ask myself, when is this true? What would I have to put in for x to make it be true? There's got to be something, right? For instance, I know that sine of pi over 2 is 1. So sine squared of pi over 2 is also 1. So there is values that make it be true. Just wonder what else I would need. So let's get started with some very simple questions. Well, simple, but maybe not easy based on what we have with us so far. For what values of theta is sine of theta equal to a half? Is cosine theta equal to a half? Is tangent of theta equal to a half? Well, I know that sine of pi over 6 is a half. I know that cosine of pi over 3 is a half, and well, tangent doesn't have a nice value to get to a half, right? Pi over 4 would be, tangent of pi over 4 is 1. I could also get to square root of 3 or 1 over the square root of 3, but that's pretty much as close as I can get for the nice values off the unit circle. So I know the arctangent of a half gives me pi over 6, arccosine gives me pi over 3, and arctangent I would have to look up on a table or use a calculator and get about 26.5 degrees or 0.4636 radians. But that can't be all of the values of theta that would solve these equations. There's got to be many, many more. So let's start with the first one. Start looking at sine here. So here's 1/2, right? I'm trying to solve sine theta equaling 1/2. So here's 1/2, and here's sine theta. And I said already that, well, there's pi over 6 right there, and that does give me a half. But I've got a lot of other intersection points with the sine graph here and y equal 1/2. So maybe you recognize, oh, well, you know, sine's periodic with period 2 pi, so I can add 2 pi or subtract 2 pi as many times as I like and I'll get another solution. And that's true. But I've got something else here, right? I've got a few more that I can't get to just by adding 2 pi over and over again. You'll see that I go from pi over 6 to 5 pi over 6. I go from 13 pi over 6 to 17 pi over 6. Negative 11 to negative 7. And then whatever this is, like negatives 19, yeah, negative 19 pi over 6. So there's a lot. And right, I can keep sliding this to the left or to the right, and I'd probably find more as well. So how do I find all of these solutions? Well, what I can do is I can say, well, I know that if I'm in the first quadrant, I have some theta value that would get me a sine of theta equaling some number. But if I'm in the second quadrant, I have another one that's going to give me the same sine value. In general, if it's sine theta is some number, then sine of pi minus theta gives me that same number. So that's how I go from the pi over 6 to 5 pi over 6, right? Pi minus pi over 6 is 5 pi over 6. Pi minus 13 pi over 6 is, well, something. 7 pi over 6, something like that. It's something else. You know, it works. Hush. So that's how you go from pi over 6 to 5 pi over 6. And then you add 2k pi, right? You add 2 pi, 4 pi, 6 pi, 8 pi. You subtract 2 pi, 4 pi, 6 pi, 8 pi, and so on in both directions. And that's how you go from this solution here at pi over 6 to pi over 6 plus 2 pi, pi over 6 minus 2 pi, pi over 6 minus 4 pi. And that's how you get all of these infinite solutions. And then the negative theta plus pi, that's the 5 pi over 6. You then add 2 pi to get here, or you subtract 2 pi, and that's how you get all of the possible solutions for sine of theta equaling 1/2. And so we use this letter k here just to be an integer. It's any and every integer. So theta, pi over 6, plus 2 pi, plus 4 pi, plus 0 pi, right, if k is 0. And that gets you all of these right here. And then also 5 pi over 6 plus all of the even multiples of theta gets you all of those guys. So that's how you get all the solutions for sine theta equaling 1/2. And here we have something very similar for cosine. You get some value, right? We had pi over 3 being satisfying to cosine theta equaling 1/2, but 2 pi over 3 is not going to work, right? Pi minus theta is not going to satisfy the same equation. Instead, you have to remember that for cosine, you don't have the same property you have as sine, right? If theta satisfies the equation, it's not pi minus theta that's going to work. It's going to be negative theta. And so what we can do is we can take this guy and slide it 2 pi, slide it back 2 pi, and for this one right here, we slide it forward 2 pi, slide it back 2 pi, and keep sliding both of these forwards and backwards as many increments of 2 pi we want, and that's got all of our solutions. So our first set is whatever worked the first time, whatever arc cosine gives us, which is pi over 3 in this case, add 2k pi, add all even multiples of pi, and that gets us half of our solutions. The other half is negative theta, which is negative pi over 3, which we could also refer to as 5 pi over 3. Those are coterminal. And so negative pi over 3 plus 2k pi, where k is any integer, or 5 pi over 3 plus 2k pi, where k is any integer. And lastly, we have tangent. And tangent's actually not that bad, comparatively speaking, because tangent doesn't have a lot of tricks to it. Tangent is periodic with period pi, and so you don't have any of these issues. You just say, okay, I've got whatever works for arctangent, and then I'm just going to add every integer multiple of pi I want. So 0.4636 plus pi, plus 2 pi, plus 3 pi, plus 4 pi, all of those are going to be all of your solutions. And so that's how you would find tangent. In general, and you're going to want to hold on to this information, if you're using arcsine to find a value, a solution, you can take your one solution and turn it to infinitely many solutions by adding 2k pi to it, and also finding negative theta plus all the odd multiples of pi. Right? That's kind of how we can rewrite what we had before with arcsine. With arccosine, it's plus or minus theta, and then plus all the even integer multiples of pi. And then finally for theta, you just add all the integer multiples of theta. And all the integer multiples of pi. And that will give us everything we want. These are all of our general solutions. And in the next video, we will look at how to use this. So look forward to it.